Okay, so I've highlighted a few of these. I think I did the same thing for exam 1 that I thought were representative of the type of problems you may see. So before I get started, does anybody have any specific problems we need to address in these 3 chapters so that we can get your concerns addressed before I start talking? No? Do we even need to do a review?
Yeah.
Okay. Number 1, for the benefit of our recording audience. Elements in group 1A and 7A of the periodic table possess respectively how many valence electrons? If you use the Roman numeral system, where you have alkaline metals are Roman numeral 1, alkaline earths are 2, boron group is 3, carbon group is 4, pnictogens are 5, chalcogens are 6, and halogens are 7. Those Roman numerals tell you exactly how many valence electrons there are in that family, right? So 1 and 7 means 1 and 7 valence electrons. Okay, that's why the answer is B. They 1 and 7. Okay. Now, I know when you worked on the periodic table and filled it out for the extra credit, we had the new system where you just numbered 1 through 18 across the top. This is an older system, and in many respects, it's more useful because of that fact. Okay, let's see, 2. Formation of a positive ion is the result of an atom, what? How do you form ions? In this case, yes, it's the balance of the protons and electrons. And you can't touch the protons, not in a chemical reaction. You can in a nuclear reactor, but that changes the element. The number of protons determines the element. So if you want an ion of that element, you can't mess with the protons. The only way that you can get a positive or a negative ion is to either, for positive ions, subtract electrons or add electrons for negatives. Okay, so that's why the answer is lose 1 more electron. Lose an electron. So if we have something with, I don't know, sodium has 11 protons. It also has 11 electrons if we're neutral, right? So if you lose an electron, now you only have 10 electrons. You have 10 negatives and 11 positives, means you're positive 1. Okay, that's how you make an ion. Now, which elements in the periodic table prefer to lose electrons and make positive ions? You have 2 choices, metals or nonmetals. Right, well, sodium's a metal, right? I just made a positive ion out of it. Metals make positive ions. Nonmetals make negative ions when they're reacted with a metal, because you've got to transfer the electron completely from the metal to the nonmetal, like sodium to chlorine to make sodium chloride. If you have 2 nonmetals bonded together, what do you got? You don't have ions, right? You have a covalent compound. Okay, I'm expanding on the question. All right, so let's see if I can scroll up. Number 3. How many total electrons are present in this ion How many total electrons, right? Watch every word in the question. Well, how many electrons do you start with when it's neutral? You go to your periodic table. Nitrogen has 7 protons, right? So you're starting off with 7 electrons, correct? Well, we just added 3. So you should have 10 electrons, correct? That's how you got that one. Is anybody having trouble with these concepts? No? Okay, that's good. Elements in group 2A and 7A of the periodic table. I got that in the way now. Come on. I'm gonna have to get rid of that. There we go. These elements are expected to form ions with charges of what? Okay, if you're in the second, if you're 2A, what column is that? The second column, positive 2, right? Let's see, this is 4. So 2A would give you a positive 2 charge, alkaline earths. And the 7 would be which group? The halogens, right? Did I read that right? Yeah, 7A. So what are their preferred charge is -1. Add an electron to those, subtract 2 from that group. Let's see, I gotta scroll again. Oops, somebody talking? Oh, I'm talking. Let's see, again, couple on this one. They're all bunched together in the front. We'll do every one for a little while, and then we'll start skipping some because they're repetitive. The correct formula for the ionic compound that might be formed from sodium and arsenic is what? If we want to make sodium and arsenic in a compound, can we do that? What's sodium? Metal. What's arsenic? Looks like a non-metal. Actually, it's a metalloid. It's one of those that can go both ways. So sodium's in the first group. If it's going to have a charge, what will it be? Arsenic is in the same group as nitrogen. If it's going to form an ionic compound, it will have what charge? Start with the halogens, -1. Next one left to it's -2. Next one left to it's -3. The nitrogen groups, -3. So how do we balance that? With subscripts. 3 times +1 is a +3. Balance is a -3. Okay. Now, what do we call that compound? What is it? A type 1, type 2, or type 3? It's not a type 3, right? Because you got a metal and a non-metal. So it's either a 1 or a 2. So what distinguishes 1s or 2s? Charge on the metal. Can sodium be anything but +1? No. So it's a type 1. So that means all we have to do is say sodium arsenic, right? What's the ending? Y'all are putting me to sleep. Arsenide. Sodium arsenide is the name of that compound. Okay, number 6. In which of the following pairs of compounds are both members of the pair ionic compounds? Okay, so you got to decide what's the best way to decide. Metal, non-metal. Are both of them metals and non-metals? Look at A. Phosphorus and iodine. They're both non-metals, right? So you can throw that one out. H2s and NCl3. Well, N and Cl, chlorine, they're both non-metals, so you can throw that one out. They both have to be ionic compounds. Lithium and fluorine, well, that's ionic. H2O, that's a covalent compound, right? Hydrogen's kind of unique, right? It's not a metal or a non-metal. So it can go both ways. But in this case, we know that water is a covalent compound. So pick the best answer. Lithium and iodine, yep, metal, non-metal. Nickel and oxygen, metal, non-metal. That's why the answer is D. Both of those are definitely ionic compounds. All right. Oh, there we go. What's the correct name for this ionic compound? So we even tell you it's an ionic compound. So you don't even have to think about type 3s. It's either a 1 or a 2. Let's see, number 7. Yes. 3, right? Okay. How do you tell? If you know it's the difference between type 1 and type 2, how do you tell the difference? Look at the metal. Can the metal have more than one charge in various compounds? Where does iron come from? It's a transition metal, right? And all transition metals except for 3 of them can have multiple charges. And iron is one that can have multiple charges. See, what are the ones that have single charges? Zinc, cadmium, and silver. Right, so they would be considered type 1 compound material. So iron can have, we're going to name this one, and how do you name a type 2 compound? You write the metal, then you leave a space for the charge. Then you write the non-metal. What's Se? Don't remember. Selenium. So we add an IDE on the end. Selenide. Now we got to figure out what's the charge on iron. Well, where does selenium come from? Right? Did you find it yet? Look in the chalcogen group. It's the third one down. Oxygen, chalcogen. Oxygen group. Yeah, if you did the extra credit, then you know that's a chalcogen group, because that was one of the things you had to put in your table. Oxygen's -2, sulfur's -2, selenium's -2. So we know this one has to be -2. So what's the total negatives here? 3 times -2, -6. That means this has to balance that, but you got 2 of them, right? So each one is a +3, right? 2 times +3 is +6. There you go. Iron 3 selenide. All right, 8. Which of the following statements about polyatomic ions is correct? What's a polyatomic ion? Nobody? It's a collection of atoms that are covalently bound, and they act like a single unit ion. Can't break them apart. Charge is distributed over the entire group, such as nitrate or sulfate or hydroxide. Right? These are covalently bound atoms in here, and they have a charge on the whole group. And that group acts like, in this case, the anion, right? The right-hand side of the name. So which one of these fits that? All have names which end in ATE. Is that true? No, it's not. They have, some of them do have ATE on the end. A lot of them have ITE. Some of them have I plus a hypo in front, like this one. Hypochlorite. Put a sodium on it, what do you got? Well, maybe a 6% solution. Bleach. Chlorine bleach. Right? You didn't know there was chemistry in your house, did you? Oh, that's not right. All must contain one of the halogens. Well, that's not right. I just showed you sulfate, right? Sulfur and oxygen, neither one of those are halogens. So I would throw that one out. How about negative ions are more common than positive ions? Yeah. In fact, there's only one positive ion in our whole group. Remember which one it was? Which is ammonium. That's ammonium. Okay, so C is the right answer. And all carry a charge of 2. To what? It doesn't matter because they have various charges. All right, so C is the answer to 8. Let's scroll up. See if we can catch 9 and 10. There's 9, but I can't see the words now. All right. The formulas of the sulfate. 9. The formulas of the sulfate ion, nitrate ion, phosphate ion are respectively. Right. So I didn't have you memorize them, but your test will have the list. All you got to do is go find them in that list. So the sulfate ion is this one. We showed that one already. Actually, we showed the nitrate also. And the phosphate, we didn't show that one. PO4 3 months. Okay. So that's why the answer is D. Let's see, 10, yeah, 10. I wonder if I can get rid of that bar at the top. Yeah, there we go. In which of the following pairs of ions are the 2 members of the pair isoelectronic? What does that mean? They have the same electronic structure, don't they? Remember how we wrote the structure, the electronic structure for our ions? So if we do A, that one, how do you write the electronic structure? Was that in one of these chapters? Yeah, we didn't do it for the first test, did we? It's for this one. You start with the neutral atom, and then you make an ion out of it. So with sulfur, it's got what? 16 electrons, 16 protons, 16 electrons to begin with, and then we have to add 2 more, right? Let's see, that's 10. We need 6 more to make the neutral atom. 3p what? That's 10. See, 10, 11, 12. Can we put 4 in here? Yeah, we can put 4 in there. How many can you put on a p? This many. Okay. So that's the neutral atom. So if we add 2 more electrons, where are they going to go? They're going to go right there. Right? So we can say that and do that. Okay, how about chlorine? How many in chlorine? 17. Okay, here's a quicker way to do this. What are these elements doing when they add or subtract electrons? They're trying to look like noble gases, right? That's a noble gas because everything is full. So what is that noble gas? It's isoelectronic with the noble gas argon, right? And chlorine is adding 1. It's trying to look like argon. So this one has 2 members that are isoelectronic. Everybody see that? Yeah. Turn your glasses sideways. Okay, so that's A. How about B? Sodium and potassium. When sodium loses an electron, what does it look like? Neon, right? Just use your periodic table. So it looks like neon. How about potassium? It looks like argon. How did I do that? I subtracted 1 electron, and that made me back up to the next period above it, over to the very far right. Where's my pointer? So I went from here, take away an electron, it looks like neon. Right? I went from 11 to 10. Potassium, I went from 19 to 18. Right? So those are not isoelectronic. So we throw that one out. How about C? Aluminum and nitrogen. Al3 plus and nitrogen 3 minus. So how do you, with aluminum, you want to work backwards because you're losing electrons, right? Aluminum, lose 1, magnesium, sodium, and then neon. So this one looks like neon. How about nitrogen? Nitrogen, we add 3 electrons, so we go to the right. Nitrogen, oxygen adds 1, fluorine adds 2, neon adds 3. So those 2 are correct, and that's why D is the answer. More than 1 correct answer. Okay? Did I lose anybody? Anybody going to admit that I lost you? All right. 11. Which of the following elements would be expected to form a monatomic ion with a charge of +2? So we need something like that with a 2+ charge. Monatomic, right? Only 1 atom. Is oxygen going to form +2? It's a non-metal. Right? Sulfur. No, it's a non-metal. How about magnesium? Yeah, it's in the second column. So magnesium is a good answer. We don't have to go any further. That was 11. Okay, we're going to start skipping some now. They're repetitive. 14. Which of the following pairings of compound name and compound formula is incorrect? All right. Sodium oxide. Sodium oxide. We need sodium and we need oxygen, right? Metal, non-metal. What's the charge on oxygen when it's in an ionic compound? Right? What's the charge on sodium? Does it vary? No, it's the first column. Always a +1. Right? So you need two of these. Na2O. That's correct. We're looking for the incorrect one. How about magnesium sulfide? Magnesium and sulfur. Okay, let's balance it. Is this an ionic compound? Did they tell us that? They didn't tell us it was ionic. Why is that sticking up there? I don't know. We are recording, aren't we? I hope. Okay, where's sulfur? Sulfur's in oxygen's group, so its charge is always what? Right? About magnesium. It's an alkaline earth. Second column, 2+. So that's it. One magnesium, one sulfur. So that was wrong. We found our wrong one. More than one correct response. Why would we say that? We're looking for the incorrect one, right? Oh. No? 14D says more than one correct response. Which is true. But it doesn't answer the question. The question was find the wrong ones. You got something for me? Oh, okay. Stapler's over here. All right. Okay. So multiple choice. Always pick the best answer. Even if you think two of them are good, look for the best one. That was 14. Which of the following compounds contains more than 10 atoms per formula unit? Okay, 10 plus atoms. All right, so let's write the compounds. A, ammonium phosphate. Ammonium phosphate. Right? They're both polyatomic ions. This is a 3-, this is a 1+. So with polyatomics, the only way you can balance them is if you need more than one, parentheses. You can't change the subscript of a polyatomic. Right? So we need 3 pluses, right? So NH4 taken 3 times and 1 PO4, that's the compound. So do we have, how many do we have in here? That's 3 plus 12. Yeah, that's more. Okay, there's 1. B, aluminum carbonate. Aluminum carbonate. Aluminum has a +3 charge. Carbonate has -2. Right. So how do you balance an odd and an even? A lesson from math class. Cross multiply. Bring a 2 over here and the 3 over here. 6 plus, 6 minus. So let's see, we have 2, 3, 4, 5, and 9 is 14. There's another one. How about iron 3 cyanide? Cyanide's a polyatomic ion, but we need 3 of them to balance that plus. Right? So 3, 6, 7. That's not more than 10. Okay, that's it. So we say, all right, we found 2, more than 1 correct response. That's your answer. It was 15. Let's scroll. 19. Oh, we had some of these on the first one, didn't we? I put all of this type of question, I put all those in the bonus, didn't I? Okay. How am I doing on time? I got to shut up at 11. I got an hour. I'll tell you what, let's skip this type of question for now, since I'm pretty sure they're all bonus. And we'll come back to them if we have time. These guys? Yeah. I think that's why I put them in the bonus. In the beginning, some unlucky class ahead of you got these in the required section, and then I realized that they were too much. Okay. All right, how about this one? 21. For the electron configuration, there it is. Choose the appropriate number of valence electrons present from the response list. All right. Let's see, I'm going to try to use my pointer here. So if we look at this thing right here, what are the valence electrons? Where do you find them? You find them in the highest energy level electronic configuration. And that means the highest number n. All right, so if you have 1s2, the number n is 1. 2s2, the number n is 2. So you look for the ones that are all, in this case, 3s, right? And count them up. So you have 2 from the s and 5 from the p. That's 7 valence electrons. That's why the answer is D. Okay? 22. For this electronic configuration, choose the appropriate number of valence electrons present from the, oh, okay. So this one is kind of funny, actually, because it goes 4s2, 3d10, 4p3. Technically, the 3d10 is a higher energy level than the 4s2. That's why it's in that order. But for valence electron purposes, we still go to the highest n number, which is 4. So you've got 2 in the 4s2 and you got 3 in the 4p3. That's 5 electrons. That's why the answer is C. All right. 23. Do we need to do this one? For the ion or element combination M2 plus X minus, choose the correct formula. All right. So you just balance the charges. You need 2 minuses, correct? So it's MX2. That was easy. (24). Are we going to do another one? Choose the correct formula of the compound formed when M. Oh, okay. So you have to work a little harder for this one. M comes from group 3A. Right. M comes from 3A. And X comes from 6A. X comes from 6A. Okay. So how do we deal with this one? 3A is obviously a metal. Right? If you look up there, 3A is the boron group. So what are the charges there? Well, think about it. What are these elements trying to do? They're trying to get to 8, the octet. Is it easier for this one to lose 3 electrons or gain 5? It's easier to lose 3, right? So that makes it a 3+ charge. This one, it's easier to add 2 electrons and make 8. So that makes it a 2- charge. Now you just balance the charges. M2x3. Okay. That one took a little more work. That's the kind of problem I'll stick you with on the test. Because you have to think. Up 25 and 26. We can get those on there. Choose a formula from the response list where a greater number of negative ions are present than positive ions. Oh, you just have to look at it. Right. K3N. If this negative and that's positive, there are more positives than negatives for this one, so that's not it. How about this one? There are more negatives than there are positives. That's a good answer. What about this one? Calcium sulfate. Okay. This one's a positive 2. The ions here, this one is a polyatomic. So you don't look at individual atoms, you look at the whole group. That's 1 negative and 1 positive. Actually 2+ and a 2-. So that's not it. And how about this one? NH4 2S. That's a plus, that's a positive, right? It's on the left, cation position, anion position, one of these. So we got more positives than negatives, that's not it. So this is the only one. And that would be B. 26, choose the polyatomic ion that contains a total of 4 atoms. So here you have the name and you got to associate the formula with it. Hydroxide ion. Nope, that's only 2 atoms. How about ammonium ion? Remember that one? We just put that one up there. That's 5. That's not it. Nitrate. Yep, that's 4. Sulfate. That's 5. Okay. So nitrate's the answer. Let's see, scroll to 27. Yeah, we'll put 27 right there. 27. Choose the polyatomic ion that contains 1 hydrogen atom. That works. And test-taking technique for multiple choice. If you have unique answers for each one, you don't have any of those squirrely ones like 2 of the above, none of the above, that type. You just got just straight answers. Once you find your answer, you're done. That's 1 hydrogen atom. You're good to go. You can go through the rest of them if you want. Nitrate doesn't have any hydrogen. Sulfate has no hydrogen. Ammonium's got 4 hydrogens. Right? So there it is. $29. Oops. Yeah, there it is. 29. Which of the following molecular compounds would have a Lewis structure that contains 10 electron dots? 29. All right. So everybody remember how to draw a Lewis structure? Probably faded. If you haven't been doing it, it fades. 10 electron dots. Okay. So Lewis structure. I just start at the top. If we're going to do this one, What do you do first? Add up the valence electrons, right? Okay, there's 1 there, 4 there, 5 there, I think. Yep. Okay, so that's 10. Well, that's the answer. You don't even have to draw the structure. It's going to have 10 electron dots somewhere, right? That's another goal of taking a test. Get the answer as quick as possible. Get the right answer as quick as possible. All right. 30. The total number of non-bonding electron pairs present in the Lewis structure of SiH4. Okay, this one's a little more work. So we're going to have to draw the structure here and find out which ones of the electrons are bonding and which ones are non-bonding. Okay, so silicon. It's carbon's group, so it's got 4 valence electrons. Hydrogen has 1 each, so it's 4. So we have 8 electrons that we have to deal with. All right, how do we start? Well, silicon's going to be in the middle. And then we're going to have hydrogens all around. We know that here primarily because if you put hydrogen in the middle, you're stuck because hydrogen can only form 1 bond. Right? So we have to put silicon in the middle. And then we start off here, 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 like that. Right? And those, each one of those lines represents 2 electrons. So we've used up 8. Oh, that's it. There are no non-bonding electrons in this molecule. 2, 4, 6, 8, they're all bonding. I guess that's why the answer is 0. Sometimes I surprise myself. (31) Let's see. In which of the following molecules is a coordinate covalent bond present? Okay. Remember what a coordinate covalent is? It's a bond where the 2 electrons that are shared come from one side. You don't get 1 electron from one side and 1 from the other. All right. So let's see. HCN. Let's see. That one's used up all its electrons. This has an octet. That only has 6. So it's got a non-bonding pair out there. Well, one of the things about covalent bonds is that's really not a fair question. Sort of, but not really, unless you remember our discussions in the lecture part of the course. We actually talked about this one and some others like it. Once the compound is formed, there's no definitive way to say that it's covalent. You have to know what came together to form it. And the one that's most likely, it looks like to me, and notice that you've got C has nitrogen. And then right below it is that one, which should be like this, like that, like that. So that could be a clue, right? This one is definitely not a coordinate covalent bond. But if you take this one and then add an oxygen to it, this one's already satisfied. If you bring an oxygen in here, oxygen has 6 valence electrons, right? As an element, it didn't need any more. But as it turns out, it took these 2 and made a bond out of it. So dinitrogen monoxide is a coordinate covalent compound. I don't know if that helps, because there's not a really easy way to explain this. I thought that was the best way. All right. How am I doing on time? How am I doing on, let's see, where's my copy? Huh? It was going to take the whole time. Yeah. So I need to finish on time. What I was looking for is you got a copy, hard copy there. How many more do I have? I'm only on 35. Okay. As long as I skip a bunch of them.
Well, there's
one. Okay. Let's do those. Yeah, get those out of the way. Got a number? Okay. All right, we'll scroll to 49. Oh, when we're getting into geometry. Okay. Yeah, we did. But it was just, right? It's like driving fast through a toll booth so you don't have to pay the toll. And hoping they don't catch your license plate on the camera. Okay, let's see. Compound with a trigonal pyramidal geometry. What's a trigonal pyramid? Well, it's kind of like the Egyptian pyramids, only it doesn't have a square base, it's got a triangular base. That's a trigonal pyramid. And I assume from this that that's the molecular geometry, not the ionic geometry. Okay, the first one, H2O, we know that was water, right? We do this, this, this. That would be our Lewis dot structure, right? So how many groups do we have here? 1, 2, 3, 4. 4 means tetrahedron, right? So your tetrahedron would be like this. Let's see. Oxygen in the middle. And then you have maybe a hydrogen here and a hydrogen here. And you got toward the back there, like that. And behind the oxygen, you got 2 electrons there and 2 electrons here. That's your pyramid. But if you cover up those lone pairs, you have a bent molecule, right? Does everybody see that? Okay, let me see if I draw it a different way. Like that. So that's a tetrahedron. All right, it's got 4 sides. 1, 2, 3, and then the front side is 4. Okay. So we got to put all of these things around here into that tetrahedron. I put the 2 hydrogens down here, but it doesn't really matter. You can put a hydrogen up here and a hydrogen down here, and you can put 2 electrons there and 2 electrons here. Right? Those 2 pairs. Okay. Then you got your oxygen in the middle, right? This is the geometric structure, but it doesn't show you the bonds. The bonds are between oxygen and the hydrogens. Okay. And these guys out here are on the other side of the molecule, right? Vsepr, valence shell electron pair repulsion. In other words, you put either the bonding electrons or the non-bonding electrons as far apart from each other as possible. This is the way you do it with 4 pairs. Then, if you're looking for the molecular structure, you just ignore the lone pairs, the non-bonding pairs. What do you have? You have a bent structure, right? So that's not the answer. That's not a trigonal pyramid. Huh? No, that's only for the electronic structure. And then you go from the electronic to the molecular structure. And in order to do that, you ignore the lone pairs of electrons. Okay, so that was not it. How about B? N, N, O. And here. Okay. So what do we have here? With two pairs around this one and two pairs around this one, those are linear. And out here, well, actually, this is linear too. Once you get past the lone pairs, that's all you can have. This whole molecule is linear. Okay, how about C? pH3. Okay, this is the Lewis structure. Okay, so you got four groups, 1, 2, 3, 4. That's another tetrahedron. So if we draw the tetrahedron in here like this, and we put, say, hydrogen here, hydrogen here, hydrogen here, and then the phosphorus is up here in the middle. So the bond is here, here, and here. And the lone pairs are up here. So now what you have is a triangular base with a pyramid. That's your trigonal pyramid.
So that's a coloration.
Yeah, I mean it's like you got a triangular base. Triangular base. You got a phosphorus here, got a hydrogen there, hydrogen there, hydrogen there, and so you got a triangular base with a phosphorus at the apex. That's a trigonal pyramid.
So will only compounds that have 4 parts to them be?
I hate to say never or always. Most often, you'll see the kind with if it starts out as a tetrahedral electronic structure with one lone pair, that will always be a trigonal pyramid in the molecular structure. Ammonia is another one like that. And that fits because nitrogen and phosphorus are in the same group. I bet there are arsenic compounds that would do the same thing. Okay, what's the other one? Or did I answer that one?
Yeah, but like looking at that, I would think for a triangle and
It takes a lot of work. Some people are good at visualizing three-dimensional structures and some are not. I'm not. It's taken years for me to get comfortable with it. Okay, you have another one? 55. Oops, let me go back. There we go. The formula mass of ammonium phosphite. And we give you the formula there. That's nice. 55. Ammonium phosphite. Right? So that means we need 3 of these. So they did it correctly. That's the correct formula. Okay, so the formula mass for this would be, notice that when you have a subscript outside of parentheses, it propagates through the entire group. So you have 3 nitrogens at 14.01 grams per mole. You have 12 hydrogens at 1.01. Now you have 1 phosphorus. I have to look that one up. 30.97. Right, these are all grams per mole. And oxygen. Right, you just have to look them up in the periodic table. Right, you have 3 nitrogens, 12 hydrogens, 1 phosphorus, and 3 oxygens. You didn't get what? Yeah, just one phosphorus. Oops, I did that wrong. There. This one's 4203. This one is 12.12. This one's 30 and 7. And this one is 48. I get 133.12. All right, close. Pick the best answer. Okay. Oh, okay. Yeah, that 3 only works for this oxygen. If we had had a parentheses here and something out there, then you would propagate it through the whole thing, but not in this case. Okay, any others? Where did we leave off? Okay, we did that one. All right, when we're, let's see, did I skip any important ones? Let me see. Okay. So let's go back to, here we go. How about 46? Characterize the bond that forms between carbon and hydrogen. All right, so we're just looking at that bond. What type of bond is it? And we're talking about, is it ionic? Is it covalent? And if it's covalent, is it polar or nonpolar? So there was a chart. Did I show it to, was it in the PowerPoints? I think there was one. What you do is you take the 2 atoms and you subtract the smaller electronegativity. That's what those numbers in parentheses are. Those are electronegativity. Subtract the smaller one from the bigger one and look at this chart and see what character of the bond is. Bond polarities, here it is.
What chapter are we doing?
5. There it is. It's on page 12 on right here. So that arrow that we see there is divided into 0.4, 1.5, and 2. These are nonpolar covalent. These are polar covalent. These are ionic or polar covalent. And these are ionic, pure ionic. This one is where you have to decide. If you've got a metal and a non-metal and it comes out in this region, it's ionic. If you have 2 non-metals and it comes out in that region, they're polar covalent. Okay, so with this information, this one is 2.5 and this one's 2.1 electronegativities. So you subtract that one from that one, you get a 0.4. A 0.4 It's right on the borderline between nonpolar and polar. So I think if it is that number, it's nonpolar. Right, that's why the answer is B. It's covalent, yeah. Oh yeah, it's covalent. When we say polarity, it's always referencing covalent bonds. If we say anything about ionic bonds, it's just they're ionic. Okay. We only worry about polarity when we have a covalent bond. All right.
Is it non-polar or is it,
It's polar.
so it is?
Yeah, it's polar. So if it's 0.4 or less, it's nonpolar. The next one, 47, let's see what it does. Lithium and oxygen. Lithium at 1.0 and oxygen at 3.5. So subtract those together, you got 2.5 is the difference. So 2.5 is here. That's definitely an ionic bond between these two. Okay. We did 49 already. Let me make a note here, 51. I'll come back to that one. I'm going to go all the way to the end. And be sure that we're not missing some important stuff. Work backwards. What's the molecular geometry of H2s? H2s is like H2O because sulfur and oxygen are both in the same family. So it's going to be a bent molecule. If you draw the Lewis dot structure, it's going to look like, let's see, 81. It's going to look like that, which means electronically it's a tetrahedron. But if you cover up the lone pairs, you got a bent molecule. Now, I'm not sure if I ask anything about bond angles. The ideal bond angle in a tetrahedron is 109.5 degrees. But this one's going to be less. Why? Because of those lone pairs. I memorized it. yeah, that's one you just have to know. I mean, unless you're a mathematician, and then you learn all the angles in these geometric structures. But I wasn't. So I just learned this one. The rest of them are pretty easy. They're either right angles, they're either inside a 109.5. What I was saying was, it's not going to be 109.5 because you got two lone pairs. When you have electrons that are not bonded, they're not confined in a bond. So they tend to balloon out and they put pressure on these other bonds. And they shrink it. It's probably in the neighborhood of 107 degrees. Let's see, I'm not finished. Oh yeah, I am. H2S, it's bent. That's a bent molecule, just like water. Oops, we're going backwards. Use the balanced equation for the combustion of ethane. How many molecules of O2 that react with 2 molecules of C2H6? This is a balanced equation already. It tells you that. So How many molecules of O2 react with 2 molecules of CH2? Just look at the coefficients. 7 molecules of O2 react with 2 molecules of ethane. That's why the answer is B. Okay, you can knock that one out in 10 seconds or less. Select the set of coefficients from the response list that correctly balances the equation. Oh, yeah, this we did balance equations in this one, didn't we? Okay, so we should do that one, shouldn't we? Yeah. All right, 77. So the unbalanced equation for this one is CH4, which is methane. And I leave a space for the coefficients. This one is C3H8, which is propane and hydrogen. Okay, remember our budget method? Carbon. We're going to account for the carbons to start with and then start bringing them together. Hydrogen. That's it. That's all there is. Right, on this side, we have 1 carbon and 4 hydrogens. On this side, we have 3 carbons and 10 hydrogens to start with. What's one of the tricks? If you've got an element on either side, save it to last. Save this one to last. So we're going to get the carbons balanced first. Right, we need 3 carbons over here. That makes 3, but it also changes the hydrogens to what? 12? Okay. Now on this side, we've got 8 hydrogens already, so we need 4 more hydrogens, correct? That would be 4 plus 8 is 12, and we're balanced. Okay. Did I blow by you on that one? Okay, so what's the question? The set of coefficients. 3, 1. Don't forget the ones that's implicit. Implied. That's a 1. 3, 1, and 2. Okay.
Don't erase that, you know.
Okay. All right. Let's see. '76. Contrast the magnitudes to 3 significant figures. Molecules in 28 grams of N2, molecules in 28 grams of O2. Oh, okay. That's worth doing.
Okay.
Well, yeah, I'd say. '70.
Yeah.
Okay, 28 grams of N2. 28.
Yes. Oh my God.
Yeah, they've always been there. And 28 grams of O2. Okay, what are we going to do to determine the number of molecules? We need the molar mass, right? We're going from mass to numbers, so mass to moles is a logical approach. So we would need to get rid of the grams and leave us with moles, right? So oxygen is 2 times 16. Yeah, 32. And nitrogen is 14.01 times 2 is 28.02, right? Now, look at the question. It says, oh, this is 1, and this is Roman numeral 2. So the answers say 1 is greater than 2, 1 is equal to 2, 1 is less than 2, and 1 and 2 can't be compared, which is stupid. We know we can do it. All right. So notice 2802 into 28 is almost 1. 32 into 28 is less than 1. So we know that 2 is less than 1, or 1 is greater than 2. That's why A is the answer. You don't even have to do the calculations. Right? Just make the comparison. Are we good? All right. I'm about out of time, I think. Oh no, I got 20 minutes, right? Or no, I have to quit a little early. 1 minute before 11. All right, let's back up and see. All right, 75 is a similar type of problem. You just work it out exactly the same way. Make the comparison. All right, there's some those. We'll skip that one. But this one. The atomic masses of helium and beryllium are 4 and 9.01. Which of the following statements are true? A mole of beryllium contains more atoms than a mole of helium. Okay, looks like there are multiple comparisons here, so we'd have to look at each one. So helium is 465. Helium is 4.0 atomic mass units, and beryllium is 9.01 atomic mass units. All right, so what does A say? A mole of beryllium contains more atoms than a mole of helium. A. So 1 mole of beryllium. Wait a minute. Anybody see the stupidity of that question? 1 mole of beryllium is equal to 6.022 times 10 to the 23rd atoms. 1 mole of helium is equal to 6.022 times 10 to the 23rd atoms. They're exactly equal, right? You don't even need 4 and 9. Okay. So it says that this mole is bigger than that mole, which can't be. Let's see if we can make sense of B. A mole of helium is heavier than a mole of beryllium. This might make some sense. A mole of helium, right? If 1 mole, how much does 1 mole weigh? 4 grams per mole, right? This one is 9 grams per mole. Right? So if the problem says a mole of helium is heavier, that's wrong. It's the other way around. A mole of beryllium weighs more than a mole of helium. Okay? So B's wrong. How about C? A mole of beryllium contains the same number of atoms as a mole of helium. There you go. That's it. All right. Which of the following is the correct step for the problem? How many grams of water will be produced from 2.1 moles of oxygen and an excess of H2s according to the reaction? Okay, this is a stoichiometry problem. So you always start with a balanced equation. Fortunately, that equation is given to us. Okay, there's our balanced equation. How many grams of water will be produced? Grams of water. So we want X grams of water. 2.1 moles of oxygen. 2.1 moles of oxygen. And an excess of hydrogen sulfide. Okay. So actually, stoichiometry problems are dimensional analysis problems. That's why the answer is listed this way. It doesn't give you a number, it gives you a process. So where do we start? We have to start with what we know, 2.1 moles of oxygen. All right. So can we go anywhere in this equation? Yeah, it's already in moles. We can move anywhere we want to. We just need a conversion factor to turn it into moles of water. Right? Cancel the moles of oxygen, leaves you with moles of water. What is the conversion factor? For every 2 moles of water, we consume 3 moles of oxygen. That's the first part of the equation. Now that we have moles of water, what do we need? Conversion to mass, molar mass. So for every 1 mole of water, how many grams is that? Oxygen is 16, 2 hydrogens is 2.02. Right? So that will get us to grams of water. Now, which one matches? Okay, they all start with this one. C? Yeah, C is the only one that matches that. Okay? Let's back up a little more. I don't know if I can make it to 51. 62. Potassium forms an oxide with the formula K2O. What is the coefficient of oxygen in the balanced equation for the reaction of potassium with oxygen to form this oxide? Okay. This is a word problem. Word problems are very sneaky. So, read it from back to front. Not what's the coefficient of oxygen, but balanced equation. Reaction of potassium with oxygen. Potassium with oxygen yields potassium oxide. Correct? Yeah. That forms the oxide. Now we need to balance it. We got 2 elements on this side, so it should be fairly easy. We got 2 oxygens here. That gives us 2 oxygens. Now we have 4 potassiums. That's balanced. If you're more comfortable doing the budget, that's fine. It's very easy. Okay, now what's the coefficient of oxygen in the balanced equation? 1. Not 0. It's 1. If you've got it there, it's got to be at least 1. We just never write 1. Okay? Let's see. $61. Can you balance that equation? We can do it. All right, what do we got? C4H10. C4H10, which is butane, right? The little butane lighters. That's the stuff they put in it. What are we going to do? Burn it? Yep. That's a combustion reaction. And we're going to make CO2 and water. Okay, let's set up our budget. Carbon, hydrogen, oxygen. That should be everybody. 4 carbons, 10 hydrogens, 2 oxygens. This side, we got 1 carbon, 2 hydrogens, and 3 oxygens. Right off, we got a problem. Odd, even. So we're going to leave oxygen alone anyway because it's an element. So let's just start at the top. We need 4 carbons, right? That changes our oxygen mix. 4 plus 1 is 5. That's even worse. Now we got 2 prime numbers. Well, we had 2 prime numbers before. Okay, now we're going to do hydrogen. We got 10 on that side. We need 10 on this side. 10 hydrogen. It messes up our oxygen again. So now we got 8 plus 5 is 13. Okay? So we need a trick. How do we get 13 oxygens here? The carbon and hydrogen's balanced. Now we just need to do oxygen. How do we get 13 oxygens out of this side? Use a fraction. 13 halves, right? Take half of that molecule and multiply it by 13. That gives you 13 oxygens. Okay? But what we need is to get rid of the fractions. They're kind of messy. So how do we get rid of that fraction? Multiply the whole thing by that denominator. Okay? 2 of these is 13, right? Are you dazed or just you following me? Okay. All right, so we got 13 there, 2 here, 8 there, and 10 there. And we used up that multiplier. So the coefficients are 2, 13, 8, and 10. That's why the answer is D. Okay? I think I said this before, but this is a hydrocarbon. Right? Hydrogen and carbon, that's it. That's what we burn in our gas tank. Well, we don't burn that. We burn octane. But every hydrocarbon reaction with oxygen, you'll have to use that trick every time, except one exception, methane. CH4 is well behaved. The rest of them, you have to use the oxygen, the fraction trick. All right. Let's see. I should be getting close. There's another one. We did that one. That's a dimensional analysis problem. That's kind of a trick question. 57. Avogadro's number of sulfur atoms would have a mass of what? Well, it's 1 mole. So you should look at sulfur. What's sulfur? Sulfur is about 32 grams for 1 mole. Just see if you know how to read the periodic table. Okay. Formula mass. Oh, we did that one already. If we could, yeah. You need to take a break, short break. You already took one? Okay. Anybody else? Okay, we can jump right into it then. All right, so I'm going to stop the share.